So the goal today is we will do the we're ambitious, try to do the static game of incomplete information and dynamic game of incomplete information. Both are humongous objects, and also we have a cost evaluation done in 10:15 to 10:30. Then I'll give you a break. So probably we'll have a break from 10:15 to 10:40. I think we'll break from 10:15 to 10:40, something like that. So 15 to 10:30 will be cost evaluation, and I give you 10 minutes for the break. So I'll be away from this period because I suppose not allowed in this room, and I'll stop the Zoom record, and then please remind me to restart the Zoom. Otherwise, I forget. Then it's gone. It's gone. Okay. If you want to get back, I cannot. You can just ask me to do it again, but it's not the same thing anyway. I guess I can try to start to talk about this. And to be honest, even if I spend whole semester talking about these two games, it will be not sufficient. This is a big thing there. And those who do finance properly will look at this very seriously, because basically what the finance is, right? Because finance is, if we learn, right, the general equilibrium or equilibrium framework is like when there's no information asymmetry and a lot of people trading, and the price, equilibrium price would achieve in the market relatively quickly, right? But when the case there's uncertainty, then the trading will take times, right? Because of the information revelation that between traders actually is reviewed through the actions, and people update their beliefs, right? There's some Bayesian learning process and there are many things there. And information is recently a big topic that is done in the Ph.D. research. So how can I say it? Because I try to look at papers that people written in the past few years, because I'm one of the hiring committee in our department. So we hire junior people, and I would say at least half, or at least 1/3, more than 1/3, or around half of people actually doing incomplete information in the idea what we call the information design. So it's the idea that here we take, I mean, in this class we talk about information asymmetry. Some agents have more information than other, right? The question is the recent development in econ, which we don't cover, is like, is the principal or some designer or the firm, you're able to commit to design how the information is reviewed to people. Okay. For example, what does that mean is like you might be able to hire a third-party agent to do a product test, right? Then you can more or less decide how rigorous is the test done by the third party, right? Then you decide what kind of information you get, right? Whether you want a more type 1 error or type 2 error. So this kind of thing, right? If good news, it will be a good news. Bad news will be silent, right? Is it possible to design something like that? And that would be a lot of research has been done on this. Okay, and or another recent hot topic is about, say, recent 10 years again, it's like networks, right? We don't model it, it's social networks, right? It's how people that actually not interact with everyone at the same time, right? You interact with people you know, right? It's like marketing is like word of mouth, right? Or rumor that spread in the market is finance paper that a lot of people talk about, the propagation of the information. And in that case, there's kind of thing how you design the network is an issue, right? Or you talk about the recent finance paper, okay? And that's why it's a huge topic. We just do a very scratching the very little surface on it, okay? If you want, you will be a huge topic. So, but I try to give you the basics of these models, okay? So again, we focus on a very special type of modeling, which is also still very commonly used. Is what we call imperfect information. the idea is how can we model the game we don't know, and which is called incomplete information, right? We don't know. And the way to proceed is not to say we don't know, but we just don't know which one may realize. Okay. Instead of saying I don't know what is my opponent's cost, if you're talking about competition, right? Is every firm may have a private information about the cost of production, and I don't know my opponent's or my competitor cost of production, how we are going to solve this model, right? Because you don't know that, how can you decide the payoff? What is the threat, right? I don't know which my action take would lead to what payoff I have, right? So how can you model this? So Hassani actually has a very clever way to do the trick, is to consider your opponent actually have different types, okay? And it is the nature who do a lottery to decide which type they are, okay? And the nature, as what we call, has a common prior. We believe that we have a consistent belief that what kind of type that can be drawn, right? There, okay? So that is what we call the common prior, common belief assumption, okay? So in the formal sense, actually, the difference between complete information and incomplete information is about, beside the type, is a belief, okay? And in this static game, the belief is exogenous, okay? The belief is given as part of the model, okay? It's not endogenous. And in the topic 8, which we'll cover at the second half of the class, that can be dynamic, in the sense that the agent with information advantage, what they do will convey the belief, okay? And actually a lot of things doing is conveying this belief, right? That's why you see some people do stupid thing, right? And that is not stupid because they try to convey message. It's very efficient. Like, I don't know, here, many of you from the mainland, right? The work culture is very different from Hong Kong. Is people go home when they go home, when they can go home, right? Go to the work, right? And say at 6 or 5 or 6, then go, not to stay, right? But in Hong Kong, many places in the office, the people stay, okay? Even though they have nothing to do, they finish their job, they keep staying, okay? It's like person dynamic. Who go home first will be viewed as a guy who is shirking, okay? That people stay and stay and stay until someone cannot stand and then go home, right? They stay 1 or 2 hours. Very often, right, they stay until 7 or 8 or even 9, right? Completely redundant, right? And there's nothing to do. And that's why the difference between the business sector and the government, right? The government job is very stable. No one easily can fire you. People just go home, right? But in the private sector, people keep staying. Why? Right? Because you want to show you are actually very hardworking employee. Even though there's nothing to do, you stay there. Okay? So that is what is the action try to review the type. Okay? And we're going to talk about this later when we talk about, but here we take the belief as a given. Okay? So we said the belief is exogenous. What do we mean by that? It means we start with a common, what we call the joint distribution of the types. Okay? And even though it's common, it doesn't mean that everyone have a same belief. Okay? Say if you're 2 players, you're 3-player games, okay? Firm 1 and firm 2 can have different belief about what kind of firm 3 has. Okay? Say, to make it more simple, say every firm can have high cost or low cost. Okay? Firm 1 can be high cost, maybe I write down, it's easy to think because say firm 1 can be high cost, firm 2 can be low cost. Okay? Firm 3 is what? Okay. Firm 1 might think firm 3 is more likely to be high than low. Okay. Firm 2 may also think low and be opposite, right? If they think that the cost realization is correlated, right? So if firm 1 actually is high, they may think firm 3 is also high, right? And if firm 2 is low, they tend to think firm 3 can be low. Okay. So it is possible that they are is related. Actually, this is what happened in auction, right? Is the belief is correlated in the sense that suppose you try to bid a oil field, okay? And how can you know how much to bid, right? You would try to drill a little bit and try to do a test there, right? It's expensive, but you could drill some area and see, so guess how many oil is there, right? If I figure out that there's a lot of oil, then you also think your opponent think the same because you expect that you and I have the same or similar assessment, right? If I think low, then you think it's low. So if I'm thinking I'm trying to bid a lot, then you would think the other guy also bid a lot, right? It's value to me as well. So that can happen, right? So this assumption doesn't imply everyone have identical belief, but identical ex ante, but ex post after you know your type, they can be different. Is that okay? So anyway, in our exercise, we just focus on the case where we have two agents, right? Remember the model we have. So the Bayesian game, the difference between the one that is static, sorry, the difference between the complete information and incomplete one is two things, right? Well, type and the belief, okay? But because, as I said, the belief is exogenous, right? The type is you can also not control, right? Because you are what you are, right? You cannot change. So that's why it just indeed mean that, okay, the way of modeling is just like each type of you is a different of you, right? Is independent, okay? The way you behave as you are high type and low type, you can consider them as independent player. Okay, you are not coordinating among different types, right? Because different types is different parallel universe. You can imagine in this way, right? If you're high type, you are in one universe. You're low type, you are in low universe, right? So that means that you are different type is a different guy. So you are maximizing the strategy. That therefore, when we figure out the Bayesian Nash equilibrium, is you are choosing your strategy based on your own type for each type. Each type is a player, and you're choosing action that maximize your expected payoff. Okay, it's your own type, and you're facing many possible type of other. You're choosing action that maximize expected utility. Okay, I'm trying to go to example again. Hopefully that would convince you this is a good one. Okay, so here we make the very simple case. Firm 1 has no incomplete information, but firm 2 has two types: high type theta, low type 1 minus theta. Okay, and firm 1's belief is common knowledge. Okay, and what does that mean? Is firm 1 has belief like this, and firm 2, although he would know when he decide which course it is, he would know firm 1 would believe him theta is high type and firm 2 is low, and so on and so forth, right? And here the maximization problem for firm 1 is firm 2, because high type and low type are different parallel universe. Okay, so that's why the maximization has to be a function depending on his type, right? But actually doesn't mean that actually is a two player, right? High cost player and low cost player. Okay, it's a mental split between two self. So when he's high type, what he do is maximizing this. When it's low type, it's maximizing this. Okay, and so I think I correct a typo here. I shouldn't have a star here compared to your no. So this is the updated one. So this is the payoff, and this is the best response function. So you can see this one is no different from the case with complete information, right? Exactly same, nothing new, right? You go check back the slide that 2 chapters ago. This beta H and beta L these two functions is exactly the same, okay? Because firm 2 exactly know what's going on, right? To pay it to firm 2, if a high type is actually a complete information game, right? There's nothing new, okay? Depends on what the best response, depends on what firm 1 is doing. The only changes is firm 1, okay? Firm 1 actually has no idea which player he's facing, right? He has an incomplete information, and he modeled as if it's imperfect information, which he put theta as the possibility that firm 1 is high, firm 1 is high, firm 1 think him is high type, right? Firm 1 think firm 2 is high type, and 1 minus theta is firm 2 is low type, right? And then you are going to find the best response, right? He's facing this uncertainty, right? So basically, he's facing the quantity to maximize this, okay? And here is the best response. So you can see I changed some of the slides. So this is the way this best response actually depends on 2 action, right? The reason is being, as I said, you would treat actually the 2 agents, sorry, the agent firm 2 with high type, low type, actually 2 separate players. So that's why the best response of firm 1 actually respond to 2 different actions, okay? And you can see in this particular case, which is in general is not true, is if theta go to 1, okay, theta go to 1, so this term disappear. So this is exactly same as the static game, as if, okay, there is only high type for certain, means complete information, right? When this is theta is 0, that means that you are facing the low type for certain, right? So that means that in this particular case, which generally not hold, but anyway, your best response is actually the weighted average best response for when you have a complete formation, okay? Which we will see let me show you the graph, it'll be easier, okay? So I tried to draw this last night. So hopefully it's not too crazy. So maybe I just draw it here again because I think it will be less confusing because I can build it up step by step, okay? So let's come back. Let me try to draw this. So Q1 and Q2, okay? I'm trying to redraw this again, okay? So look at this, right, okay? So, oh, sorry, this would be low, so typo. So, and so look at the low type, okay? So first we draw this one first, okay? So this is A, because Q1 is 0, put that there. A minus CL over 2, right? And if Q1 is actually A minus C1, right? MSCL, right? That is 0, okay? It's linear. So here we come the first line. Which line? This is beta L Q1, okay? And you can also have the same because just QH, CH, right? So you have this one. So this is same as what we learned the Carnot, right? So this guy is beta H Q1, okay? So based on high type of firm 2, best response to Q1. Is that okay? Now, let's go to this, okay? Best response of firm 1, okay? So this is not easy to draw because actually he is looking at responding to the 2, okay? So it's the best you can draw a 3-dimensional graph, then you can work on it, okay? So what I'm trying to do is not to draw a 3-dimensional graph, okay? And because in this particular case, we can abstain from that, okay? So what I'm going to do is I will what I'm going to draw is I will draw a line, okay, which is, okay, what I'm drawing. So remember, best response for player one is respond to two number, right? High type, low type. So I can make simplicity. Let me respond to the same value, which is Q1. I just assume they're the same. Later you will see why I do that. But I just assume these two fit me the same value. In that case, because it's number between 0 and 1, right? That would be same as with the static case, right? So let me draw this one, okay? But do note that this is not the real best response, because actually you have to draw a three-dimensional one. I'm trying to say this is going to be a useful, okay? And this guy's A minus C, okay? Is that okay? Okay. And okay. Now, and the question would be, okay, what would be the actual response, okay? And look at these two outcomes, okay? These two outcomes is actually the static case, right? The static case. If you are facing the high type, for sure, take low type for sure. Okay? And given what you are doing is a linear combination, right? What it means is actually the best response would likely to be somewhere here. Okay? So this is the Q1 star. Okay? And that is and then you go it back up, right? Because someone producing this. So that means that Q2CL star is here. Because facing this is his best response. And here will be Q2 star CH2. Okay? So basically firm 1 producing here and firm 2 producing here. Okay? So that would be the best response. Is firm 1 is looking at the how to respond effectively between these two, and firm 2 is producing based on firm 1 is putting this one. This is what the best response. Is that clear? So this graph looks like this because everything is linear. Okay. So in general, this does not hold. It's not going to be like this nice form. In general, tend to be way much more complicated. Okay. In general, this may not even have closed form solution. In general, it's not. Okay. Same as Nash equilibrium, right? When you departure from the linear model, linear cost, then linear demand, then solving the Carnot will not give you a closed form solution, right? But at least we notice that this is easy to understand. Right? This is the firm 1 producing. This 2 is firm 2 producing. Is that okay? And of course, if you try to understand, it's actually just basically the three-dimensional graph, right? If you're able to think three-dimensionally, this is Q2 high type and Q2 low type. You just try to draw it. It's not easy there. So I try to, in this special case, I try to make it easier to think. Okay. Anyway, is there a question? If no, then I try to go quickly on auction, and hopefully I try to do double auction. But I think I will skip a lot of material in the auction because we don't have enough time. But I guess that shouldn't be a big issue for you. Okay. So auction, So it's an application idea, right? So basically, it's the first question goes back to the fact that why we need auction, right? And the reason is because of market is very thin, right? If you know, people from finance would know, right? A lot of, not every single asset can be traded, right? And some stocks actually never trade or very thin market. And in that case, like antique or something very unique thing, auction would be easier because like you have no market price to say, right? Just like the land, right? Each land is more or less unique. And in that sense, it's not easy to figure out how they're different, and it's not easy to come up with unique price, right? That is the reason why we want to look at auction, right? And that is one thing that departure from market is because you don't want it's unique, right? So that's why you don't want the even the seller doesn't know how much it's worth, right? So that's why he need to think how to sell the objects in a nice way. Okay. And what is so special about auction compared to others, right? And actually, this is related to more related to what we call the general mechanism design problem, which is there, say, in case of buyer and seller, right? The seller has object to sell, and a bunch of buyers, okay, who process of how much we're going to pay is unknown to the seller, okay? And the buyer don't want to tell, right? You don't want to tell the other guy what we're going to sell, right? So basically, it's the seller has a commitment, okay? He can commit it to a way to allocate the object, okay? And he actually will design a game, okay? For them to play, okay? So that's why it's what we call the economic design. That is the seller can make a game and let the buyer plays, and they will get according to the rule. Okay, so that is the main meaning, right? It's like is they enable to auction, and then that's why you see auction usually done by a third party, right? It's there's an auction house. They actually do the auction, not the guy actually doing auction, right? Because maybe the seller has no commitment to commit this, right? Because he can always say, okay, I'm trying to sell the object. If I take all people price and then I just go home and I try to do it again, right? So have to delegate it to a third party so that it's able people believe that this is a game they're playing and they will play along. Okay. And it's usually compared to two different cases. Okay, auction is another extreme. Okay. The first one is fixed price sale in supermarket. That's what we have seen, right? What we call usually the poster price is usually you will see perfect competitive market, right? You go to supermarket or 7-Eleven or any store, you're unable to talk to the owner or the seller. Okay, $10 for this. Can you sell me $9? No way he talk about it with you. This is the fixed price. You take it or leave it. Okay, there's no way you can say other way around. Okay. Okay, this is a completely fixed rule, right? And bargaining is completely flexible, right? I mean, I don't know whether if you go to Israel and go to Jerusalem, okay? I luckily have a chance to went there once, and it's going for a game theory summer workshop, summer school. When I was a third-year graduate student, I actually went there, and I think it's 2009, yeah, or 2010, I forgot. But it's very fun. I mean, if you want to go, you recommend go there. It's very fun. I mean, especially sometimes you go to the Dead Sea, you can lie on the sea floor. But anyway, this place is the old city in the Jerusalem, and where you go there, and you see a lot of souvenir shop or whatever shop there. There's no price there. Completely no price. We have to ask, how much is this? And then you talk. Okay, there's no post price. And depend on how well you are talking, it depends on price. It's very different. I mean, you go in the morning and you come back in the afternoon, can be different. Depend on how your bargaining skills. Okay, there's no post price that's completely organic, right? And this one is somewhere in the middle, right? You commit to the rule, that is the way you interact, and then you will know the outcome. Okay, so this is completely fixed price. This is completely random, more or less. It's just, you don't have commit rule. Okay, and this is auction is more or less the seller have ability to commit how he allocate. Okay, and there's a rule of the game he designed, and people play the game. Okay, and the question of say actually operation research and other people actually going to decide how to design the game. Okay, auction, I think originally they published in operation research journal or marketing science or management science. I think it's operation research journal. So originally people are from there. Okay, so auction has long history, right? Auction actually means I increase, augment, and very funny, I guess. Not funny, maybe a sad story, but one of the oldest is like auction of women for marriage. So basically, it's in the old days, like the father would bring their daughter to a market for sale, okay, for marriage, and it will go from a positive price, high, okay, and someone comes in and buy until 0 and doesn't end, get to negative. Okay, what does that mean? It starts from the price where if you want to get the girl, you have to pay positive price. Okay, and end up with if no one wants the girl, and then the father will say, okay, get the girl, I pay you so much. Okay, so you go on, and this is the, I don't know, this is one of the history. And one of the other very interesting history is the Roman Empire, and probably you know it's the empire executed by his god. Okay, and the god doesn't know what to do with once they kill the empire, right? And they said whoever gives them the highest bid will get the throne. Okay, and they sold it to the highest bidder, and of course the highest bidder basically claim, okay, every one of the god get a large piece of land, a lot of money, and of course turn out this is one of the earliest incident of winner's curse. Okay, which means that he win, and by promising a large price that he's unable to pay, and that high bidder actually got killed by this god again. Okay, so anyway, the winner's curse means that you just bid more than, okay, what it value actually get a negative payoff. But anyway, that would be the story. So modern, I mean, there's many things like IPO. I think in Singapore, one thing is interesting is COE. If you want to own a car, you need to auction for the license. Okay, and many things. I think if you ever go to the fish market in Japan, even you don't know, but you ever went to Japan, you ever notice there's a 土地市场, so that's why they sell the fish. They're very famous. And flour and government bond, everything, eBay or many things, you probably know, right? So I don't need to talk about. But I think this is one thing is also where we catch our attention. The 5G, Bob brand actually sell billions of dollars around the world. Okay. So in general, what you will learn is 4 different types of action for the auctions. One is called English auction, which is the I think it's still the most common version. Is the way of the auction is the auctioneer actually starts from the lower price. Okay, he keep increase the price. Okay, every bidder indicate whether he stay in the race or not. Okay, if the price goes up and then until the last one keeping in the auction floor, remain the hand up, then it will be the winner, right? Just like everyone raise their hand. Okay, the price keep up, and when price high enough, someone drop their hand. right? And the last one who had the hand on wins, right? But of course, in general, it's not that efficient, right? So that's why you're allowed to increase the price non-discontinuously, right? So I can say they may not need to start from 0 to 1 billion, right? $1 million, right? You can start, okay, let's start with 5 million. And then, okay, one guy thinks it's too low, it increase to 7 million, 8 million, or if you can jump discontinuously by the bidders, okay? And the Dutch auction is also still used in actually Netherlands using the flower auction, right? You actually start from very high price and drop to the very low, right? Whoever raise the hand will get the object, right? Everyone have the no hand, don't put the hand on, and the price drop like a roller coaster. Everyone who raise the hand will get the object. Okay. So that would be the two ways. Okay. And so these auction actually require everyone to be there. Okay. Everyone had to be there at the same time. Okay. And the other way around is what we call the sealed bid auction. Okay. Everyone do it separately. Everyone do it in their own room. Okay. What they do is everyone have envelope. Okay. He write his price on it. Okay. And put the envelope and put in the box, letter box, and then after the round is end, the auctioneer open the envelope. Okay. And that actually happened in Hong Kong when they sell the land. Okay. In some cases they sell land in this way. In some land they do the English auction, but recently a lot of auction done by the this sealed bid auction, and there are two ways to determine the price. Okay. Of course, the guy who write down the highest number would win. Okay. And how much price he's going to pay depends on it's a first price and second price auction. In the first price auction, you pay what you bid. Okay. And in the second price auction, you only pay, okay, not your bid, but the highest bid besides you. Okay. So in this way, suppose you have envelope, say one is 10,000, the other is 900, okay, and so on and so forth, right? 9 will be 850, so on and so forth. First price, sealed bid auction will be saying, okay, guy number A wins, okay. First price auction will say number A pays 1,000, okay. If second price auction means guy number A wins, but he only paid 900, okay. And immediately you would think, why the seller want to do the second price auction, right? Because why don't ask them to pay 1,000, right? Why the seller is so stupid, just ask the second price? The reason, after you learn so many class of game theory, is the fact that people bidding behavior will be different under different game, right? You will bid differently under second price and first price. Okay. And turn out, I mean, later we'll show. I mean, I don't know whether it will show. Actually, in general, there's no difference in terms of revenue. Okay. Indeed, these four things we have seen in general case will get you the same outcome. Okay. If players value are independent. Okay. The value I have in the object is independent of yours. Okay. But in the case that the value are correlated, as I said, with the oil drilling example where I said at the beginning, in that case, English auction is better in terms of revenue. Okay. Yes. The seller. How much the seller want to get, right? Because you are the seller, you're designing which one it would be better for you, right? And if you think you are selling antique, okay, which the price is independent usually, right? And in that case, actually the four type of auction has the expected revenue has no difference to the seller. Okay. But if you're thinking selling oil with drilling, okay, and my high value is with your high value, then these two auction, the open auction, right, is better than the sealed bid auction. Why is the case? The reason is in the English auction, say for example, it's a dynamic process, right? People actually learn information during the auctions, right? I seeing people are not dropping off, which will update my belief about what should be, right? Because if others actually not dropping out, mental not dropping out, and I would think, okay, this is worth value more, right? In that case, it actually make people would buy more. Is that clear? Oh, of course, if you want to know the real intention, then have to go deeper. But in general, this will be the main idea why you will see a lot of thing actually done in the ascending auction still, right? Because this is very costly to have ascending auction. You need to have everybody there, go there, and then just have to bid, right? And for this one, right, open sealed bid auction, it's very simple, right? Just ask everyone to write an envelope and put there, and that's it. No need to have a guy who have to say toc toc toc, right? So it's very different. Okay. And okay. And so as I said, the equivalent, okay. And not going to details, and I will talk about. I think I will talk about this late after the break. But you can see the auction is basically a Bayesian game in the sense that there's a bidders, okay, and each they will decide how much they want to bid, and they will pay off, right? You would have formed a belief of how others bidders valuation, right? Each bidder will have their own valuation, right? And the valuation decide how much they want to bid, okay? And each player will be the same idea. And what we want is to see under different type of bidding, okay, system, what they would bid, how they would bid, and which one is more superior, okay? And I would just try to say the second price is superior to first price in general, and English auction is better than the Dutch auction, but I will talk about that, okay, after the break. I guess I should go, and let me stop the recording, and once done, then so we talk about the 4 different types of auction, and I trying to claim that for seller will get similar revenue in expectation, but you do see one way of auction is more common than other, right? For the open auction is more like English type, you see more, and for the sealed bid type, right, put envelope, is more a second price, okay? So the later we will try to convince you. We focus only on the simple case, okay? We're trying to show you how bidder behave in this sealed bid auction. And the way that we didn't talk about the English auction or Dutch auction is because this not this topic, right? It's really the next topic. It's because it's a action over time. Okay, so we didn't touch in this one. But to solve these two, is we can use the method that we learned in this class, right? Which is just people do it simultaneously, right? The only thing is I don't know what other people think about how they value the objects. Okay, so that's why we can use to analyze this. And okay, and as we have actually claimed, okay, these two will give same revenue to the seller. Okay, and actually we prove what does that mean, and turn out to be the seller, sorry, the buyer, the bidder, the buyer in the second price auction. Turn out what they do is very simple. What they do is just write the value, what they think they're worth. Okay, the object value $10 to them, that's why $10. That's it. No need to underbid, overbid. But for the first price auction, what you would do is you would try to guess, okay, what is the highest among of others. You try to bid it, right? Because you want to win the object, right? If you don't get object, you have nothing, right? So what you try to do is, as long as you would, the easiest to think is what you actually bidding is you will try to expect what other guys were bidding, look at what the highest bid they can have. You just bid that amount, right? And maybe be slightly epsilon more, right? Then you win the object. As long as winning, this bid is more than, sorry, this bid is less than you're willing to pay, then you will just bid that one. Otherwise, you don't bid, right? So that would be the key. And turn out this is you would try to underbid. Okay, and the reason that you bid your own value is because you don't have to pay what you write, so there's some positive profit there, right? But if you pay what you bid in the first price auction, of course you not write the value that the actual value of the object you want, right? Otherwise you win, you have no surplus, right? So you would underbid a little bit, right? Turn out that the underbidding at the end, on average, to the seller has no difference. Okay, which is a very surprising result, as you would think, right? You would think this may end up higher revenue than this one, right? But indeed it's not. Okay, so let us start to think about this game. Okay, and in this model we have bidders and the seller. Okay, and in general the seller is not strategic. Okay, in our basic setup. Okay, the seller only committed to either first price or second price. Okay, he is not strategic. Only the strategic guys are just buyers. Okay, only the bidder strategic. Okay, and we can go back one more step to decide what kind of format they can do, but that is it is design problem. Okay, we just focus on the game setup. We have given the how they should bid, how to allocate the object. Okay, and the payoff, of course, depend on what kind of auction you're doing, right? First price and second price will give you different payoff. So we'll define that formally. Okay, and usually look at auction textbook, they would talk about 3 different types of games or setup, and these are increasing complexity. The first one is private value, so each one would have own value of the object and independent. So that's the easiest thing you can imagine. And second one is also the other extreme, is everyone have the same value. Okay, and but everyone have the imprecise estimate, right? You can imagine the oil, right? You try to drill there. The oil is unknown to everyone, right? But the total value of the oil, just the oil, the drilling is just basically the value of the oil, right? Nothing more, nothing less. But everyone have an imprecise estimate of the value, right? You can imagine the value is just like the some function of everyone's valuation, okay? But anyway, we won't talk about this. And the other one is interdependent value, right? And independent is more general, right? So everyone have their own value, but and the value I have is correlated with others. Okay, so that is the most generic is this case, right? This include these two. Okay, these two are two extreme cases, but we'll focus like all the auction introduction. We focus on the simplest case, which is the private value. So here it's an allocation problem, right? So you have a seller who want to sell an object, okay, and the object we assume has no value to the seller, so he's not strategic, right? He just prefer to sell it rather than keep it. And the end buyers, and each buyer have different valuation, and each buyer know their own valuation, but they don't know others, right? You see the object, you know how it values to you, but you don't know how it values to others. Okay, so we say in complete information, right? So we can change it to imperfect information. Everyone would think what other might think about the value, right? And the question is, the first one is how to allocate the object efficiently, right? So first is if here everyone have valuation more than 0, right? As long as someone is more than 0, the seller should not keep the object, should give this to someone, right? That would be Pareto efficient, right? Because because I did the properly, I didn't define. Do I define it properly? Okay, I didn't do it properly. So it would be the so why I say efficient, because I think I didn't write down the payoff, right? So the utility of the seller, because he has no use of the object, okay? So the only thing is, if he sell at the price P, where is price P? Okay. If so, at P, okay? Otherwise, it's 0, right? And for beta I, okay, the payoff would be just VI minus P if buy at P, right? Otherwise 0. As long as VI, right, is positive, right, it is always beneficial to sell the object, right? Because you will get some positive payoff for two players. There's Pareto improvement. Okay, so in Pareto sense, it's efficient. This efficient means Pareto. Paretian is like actually makes everyone better off without making anyone worse off, right? So you want it to, as long as someone would value it positively, you want to sell it. And the most efficient is to sell it to the highest bidder, right? For if not, the highest and the one who got it actually can have some exchange, right? To enable that happening. Okay, so that's why efficiency would require you to sell the highest value. And the easiest case, if the seller know each guy's valuation, we want to VN. That's very simple. He just simply said, okay, I set the price to the highest valuation, and that's it, right? You allocate the object and sell the highest guy, and that's the solution, right? So in this case, this is very simple, right? And this often happen in many cases, right? If I know who is going to the highest bidder, and that's it. That's very simple. There's no to think, right? And that's what happened, right? When you go to a drama, right? And the girl decide which boy to get married, and he go to the boy he loved most, and that's it. The end of story, right? It's not going to be the case that the girl go to the boy he loved the least, right? If they go to the girl loved the least, must be some other attractive area the boy has, maybe have a lot of money, a lot of power, very handsome, so on and so forth. But at the end of the day, the ultimate thing is the boy must have the total utility higher than the other, right? So that means this is the case, right? The efficient. So the question is in combination, okay? How would the seller able to sell the object to maximize his revenue, right? And also efficiently allocate. How we do is in auction usually it means that concept two parts. The seller committed to two things. He commit to the allocation rule and payment rule. What does that mean? It means that the buyer trying to submit some number, okay, price, okay, some bid, or you call bid, and the object will allocate based on bid, okay. It can be highest bidder would win, which is usually the case, right? But sometimes the rule can be twisted in the sense that you would have an, say, existing guy who is one guy that will treat them if there's no, the bid is not too much different, you favor one guy. Okay, that's also happened in, say, in supply chain analysis, right? You would try to use the guy who is current supplier if his bid is right, right? You would not, you would keep this guy as long as he's bidding the price within certain range, right? So there's also allocation rule, right? And in Hong Kong, right, how to allocate the land is what we call the one who give the highest bid will win, right? 高低价政策. So the guy who has a higher price would win, right? But this is not always the case in the world, right? Because people actually not compete on price. They also compete on the way, say, how you build the building, right? Some people will say, okay, you have a nice building, we want you there. If you sometimes say the land is going to be sold, right? You only want, say, you want a nice commercial building rather than a factory, right? So even though the commercial building may bid less, you want to favor, right? But here we focus on the case where only price, okay? But in the real world, actually, there's a lot of cases more than that, right? And the payment rule also, right, depends on what kind of the people put in the bid, right? And the first price auction means you pay what you bid. Second price, it depends on others, right? So that's what we said. An auction is, you can consider as what we call mechanism. And mechanism is a very technical term, which you specify allocation rule and payment rule is well defined, right? It's different from the bargaining, it's not well defined yet, okay? And in auction, right, it's easy to compare auction and lottery, right? Because lottery also, you are also a mechanism to allocate the object, right? So you have an object to allocate among people, right? In auction, right, you just give the highest one. In lottery, right, it is possible that you pick up the first and the second highest bid, you just do a lottery. Okay, and this happened in IPO, right? You just have a price and then you just randomly allocate among people over there, right? You just distribute. And payment rule, we have first price is highest winner win, the second bid will be the second highest. Okay, so I think this is also a base end game or and there will be possible valuation and your belief on the valuation. So let's go to actually that one. So here we focus on what we call the independent private value. Independent means everyone have the same independent value. Just like I know what I'm value doesn't tell you the other. Private means they are completely independent. Okay. So in that case, it means that everyone just need to care about its own value. Okay, when determine how much is value to you. So this we. So the simplest case you can imagine. Okay. And we also make a simplicity is every player is symmetric. Okay. So in this model, usually you focus on symmetric. So because make the model easier. Okay. That means that everyone follows the same CDF. Okay. And we normalize the value between 0 to 1. So V is basically what it says. It says VI is from 0 to 1. Okay. So that's normalization. Nothing deep in this one. Right? Symmetry, yeah, a little bit assumption here, but 0, 1 I don't think is a great deal. Okay. So what is the strategy in this auction? Okay. You would give a number to the seller and the seller decide what to do. And basically depends on your valuation. You try to bid, right? So basically just like for every valuation that you have, you just give a number. Okay. So just if say basically they said, right? If your V is 0, you probably want to bid 0. Right? You do value. If VI is say maybe half, you want to bid, okay, something less than half, but you don't know which one to bid. But anyway, that's you will decide a number there, right? You will not bid more than half, right? Because this value half to you. Okay. So it's easy to see the graph. Okay. If you bid as the value to you is what we call triple bidding. It's easy to represent your strategy by this line. Okay. For each different V, what's your bidding? Okay. And the 45-degree line means you bid what you want. If below 45, you're bidding under bidding. If above, overbidding. Okay. So the question is what you would do. Okay. So this bid shading and bid overbid. Okay. So the payoff, it of course depends on the payment rule. Okay. The payment rule depends on a vector of the bid, right? The bidding profile. And if you win, you get this one. This payment actually depends on the B. Okay. Here is pay for the B, but the P also, the P will depends on what kind of rule they given by the seller. Okay. And here I, and actually the payment rule can differentiate across different agents, right? But simplicity, you can focus on the case where they don't have I because everyone has the same rule. Okay. If the rule are applied equally to everyone, you just have no I. Okay. You lose, you have nothing. Okay. So what you do is we assume we are risk neutral, right? So your payoff would be just for the winning times the surplus of if you win, right? Because you lose, you have 0 payoff. Okay. So first, we solve the model of second price auction, and turn out to be it's very simple. The best strategy, one of the best strategy, is just truthful bidding. You bid what you think. Okay. We will justify why this is correct. Okay. So second price auction means if you bid more than everyone else, then you're the winner. Okay. And we will consider the case where the everything is continuous. There's no case that they're equal. Okay. So there's a unique winner. We don't need to worry about tie breaking just for simplicity. It'll be the same idea anyway. Okay. So The winner is like this. Okay. You can imagine that if that tie-breaking, then just the object is not sold. That's fine, because it's a zero measure event. Okay. So payment, what's going to do is, if I wins, right, he will just pay what? The highest bid besides him, right? If he lose, he get nothing. Okay. So what's the payoff? Well, if he has this valuation, the other bid B minus I, right? If he's the highest, he will get this payoff. Otherwise, he gets zero. Okay. So that would be the case, as I said, right? If they're equal, we assume that the object is thrown into the sea, but doesn't really matter anyway, because this is a turn out later. You will see this is a zero probability event, right? So that's why don't need to worry about it. Okay. And we argue that bidding what you think is actually the weakly dominant strategy. Okay, dominant strategy, weakly dominant, and turn out this is the best thing you can do, right? So what happened is we just give you the intuition, and I will try to prove it. The thing is, would you like to bid more? Okay. And when you bid more, okay, actually there's no gain, right? Because if later you will see, right, if you win, okay, actually you're paying the second highest, right? So the winning probability actually, when you want to buy the object, right, actually you actually could end up in buying at loss. The reason is, suppose you value the object like $10, okay, $10 to you. Suppose you bid 11. Suppose you bid 11, okay. You end up in a loss. Why? Because the maximum of B minus I can be, say, 10.50. Okay. You win the object when you bid 11, but you are taking a 50 cents loss, right? Because you bid this one, you're the highest bidder, but you already $10, you're paying 10.50. So you don't want to win, right? You're winning in the scenario that you don't want to win. Okay. And underbidding will exactly opposite the case, right? If you say your V is 10, if you bid $9, okay, obviously if BI is 9.50, okay, then you lose. But if you bid $10, actually you would win with 50 cents surplus, right? So of course we will try to argue this argument is right in the following slide, I think. Yes, that's the proof. Okay. So how should we read this? Okay, so this is a 9 different situation. Okay. So this is one strategy which you always truthful bidding. This overbidding, this underbidding. Okay, 3 different strategy. This is 3 different scenario. This say your valuation more than the other or other guy is bidding, right? And this is the same, this is less. Okay. So if you bid this case, other people is less than that, you win with some positive surplus. Is that clear? So everyone say, suppose it's $10, you pay $10. If it's $9, right? So you have $1 surplus, right? If you bid more than 10, you also get surplus, right? So maybe easier to think is V is 10 in the first column. Maybe I just, because this is not easy to see, maybe I just Right down here, right? To put number there, you easy to think, right? So suppose that B.I star is $9, right? Okay. You try to, your VI is 10, okay? Suppose what you bid is you bid $10, you bid 11, or you bid 9, okay? Or you bid 8, right? Make better. Okay. In this case, right, you would win, right? So you get $1 surplus. This one also win, you get $1 surplus. And this one you lose, you get 0. Clear? Right? And maybe easier to think if you bid 950, you bid 9, right? You bid 8. Okay. 950, you still win, right? You still win $1. And now you win 0, right? And less than you bid 8, you also get 0. Right? So that is what it means. That's why it depends on below, it depends on where you are. Right? And if in the second case, BI star is 10, right? So whether you win or lose, actually you have 0. Right? If you win, you pay $10. Right? You value $10. If you lose, you get 0. Right? So everything is 0 here. Okay. Suppose this BI star is 11. Okay. And it means that all this is you lose, get 0 anyway. Right? Here is if you bid more than 11, actually you would win with negative payoff. Right? If you bid less than 11, you get 0. Right? So you can see, okay, in this scenario, okay, bidding 1 is one of the best strategy, right? And in this scenario, this still remain the best. In this here, this is also the best, right? So that's why bidding what you think is good compared to other, right? There's no way that you can be worse off. So telling the truth, like this one, the horizontal one, right? This is better than this one, right? And this one, right? Is that clear? Why you would want to tell the truth, right? And this is regardless of what other people are doing, right? All the scenario. So this is the Bayesian-Nash equilibrium, right? Because you don't really care what other people are doing, right? Regardless of what they're doing, because this is summarize what they're doing, right? You don't really care about their strategy. Whatever their strategy is, I just do this, okay? So I don't really need to think, regardless of what they do. Even they're crazy, even they don't follow equilibrium, I will do what I want, right? So that's why this is much stronger than what we call the Bayesian-Nash. Actually, people call this a strategy proof or weak strategy proof. So which means that this is the best this is the best way to design a mechanism is because of the fact that player need not think carefully. They just naively say they follow the strategy, then done. So that is good thing to think about the design a mechanism or design a game, because of there's no way you can make mistake, right? If people know they're doing second price auction and they know that this is the case they apply, right? So you don't need a very high IQ to know how to bid, right? Just bid what you think, and that's it, right? There's no need to worry about it, right? You don't need to be very smart to have an equilibrium, right? Because in general, equilibrium is you need to be very smart. right? But here you don't need to, you need to think. Okay, so that is the first outcome. Okay, so that means that second price auction, the second here, you bid what you think is the next B.B.A. Okay, and we want to do the first price auction. Okay, and you will see it's very similar, exactly same, except the allocation was same, only different auction. It's not, you just pay what you bid, unrelated others. Okay, and this is the payoff, right? You just bid, you just pay what, if you more than others, you pay what you bid, right? So in general, the problem is this is the payoff, right? The only thing we know that because we pay what we bid, right? So you never bid more than you do, right? So that you can overbid. Okay, in this case, first price auction, you always underbid. Okay, and the problem is how much you should underbid. Okay, and how do you do underbid? Okay, and in general, this involves solving the differential equation. Okay, many of you would be very happy to solve this, but in our class we focus on the very simple case where, bless you, we focus on the case where we do the constant bit shading. Okay, and we'll show if your valuation actually comes from 0 to 1, uniformly 0 to 1, what is optimal strategy is just n minus over n of your V. Okay, so V depends on how many people are there. Okay, and of course you can see from this expression, right? If n is 2, right, you just bid half of the valuation, right? If you value to 10, you just bid $5, right? If you have more and more people from this expression, what you can see is n go to infinity. What's this? You just bid as if what you think, right? So if n go to infinity, what you get? Hopefully you can see it, right? When n go to infinity, right? It's just V. Why? Because that is so many people are there. Okay, basically there's no chance to win anyway, right? You bid very close to the V, so basically just like, well, unlikely you win anyway. You win with some surplus anyway, because it's infinity. But if you have n is 2, then you just underbid a lot, right? Because you know that the other guy may have very low enough valuation, you can win with large surplus. So you can underbid a lot. Okay, so that is the intuition. But we focus on the case where this is a constant one. So actually, this is what we call a linear strategy in general. Okay, we focus on the case bidder are choosing linear strategy. Okay, and that is common in when we solve this kind of game. We focus on linear strategy because of the fact that make your life easier. Okay, and in general, you want to have something like this, right? Here, I just focus on this. Probably, in general, you want your BI can be alpha VI, but you also want a gamma, a constant. Okay, but obviously, in this case, V is 0, B should be 0, so that's why it's gone. You don't need the intercept, right? So we just focus on the case only the slope. So this is your strategy. We set our attention to linear strategy. Okay, and as I said, this is a very common way to figure out the solution. But auction, you actually don't need this anyway. But if you're happy with the differential equation, we don't need this assumption. Okay. And we will try to prove, okay, one case that would be not difficult, okay. So in general, if you more than 2 agents, 2 bidders, you need what we call order statistics. But in our class, we just focus on the simplest case, which is a 2 bidder, okay. And okay, you have 2 bidders, okay. Your payoff will be, okay, everyone use the symmetric strategy, okay. Everyone will bid according to alpha of their valuation, okay. We focus on the case everyone is bidding a fraction of their valuation. The fraction is same alpha, okay. What we try to find what is alpha. Let me repeat. We focus on a special case. Everyone valuation is uniform from 0 to 1. And we assume everyone is bidding a fraction of their valuation and constant alpha. We have to find that alpha as an equilibrium. Is that clear what we're looking at? So that's why the expected payoff, okay, BI is equal to BJ, okay, better than BJ, and this is your winning surplus. And because the other guy is bidding according to a fraction alpha of the VJ, so you just replace it, okay. Why I want to do that? Because this, I can make it a subject, okay. And this is your choice. This is equilibrium parameter. This is the uniform, right? Uniform is just itself, right? Uniform of CO1, right? Just itself, right? The CDF. Okay. Is that clear how we arrive this one? Okay. So you forget about the alpha, right? BI times 1 BI, right? It's just this guy, right? If you right 0 up to VI, it's VI over 2, right? So of course you can use calculus, right? But that means that you would bid halfway, right? If you want to prove general case, because the independent, right? Your valuation bigger than the maximum of other, is just an intercept of the case you more than or n, right? So it's just multiplied by n times, okay? And just using calculus, this is what the result you get. Okay, so very simple, all right? Just how much you underbid depends on how many bidders are there. The more bidder you have, right, the less underbid, because you want to win, right? Because you lose, you get 0, right? What you're trying to bid is indeed, right, the minimum bid actually required to win. Okay, in general, that's what you're doing. Okay, you just make the bid, this bid, okay, is such that you try to win. Okay, this is the highest bid actually you are facing. Okay. So what I mean is, if everyone use this strategy, okay, that is actually you are bidding in a way such that you are exactly same as what the other opponents. Okay, but anyway, not going to. So if you want to do general, don't like the uniform, I'm not going to show it, but you can actually do the proof of differential equation and solve it out. Okay, and you will still get the same answer there. Okay, we don't. Here, what I mean is, as long as you assume uniform, okay, you can also derive the same equation without making this assumption. Okay, when I derive it, I assume people use linear strategy. Okay, but if you are happy that to solve differential equation, okay, like this, okay, we can show that without making that linear assumption, okay, without making this assumption, we still have a constant underbidding. Is that clear? As long as you believe this is uniform, okay? If not uniform, okay, you can see something similar would occur if a same differential equation, okay? But probably you don't have closed form. But anyway, you will have the same idea here. I'm not going into detail here, okay? But here I just want to demonstrate the power of the Bayesian-Nash equilibrium, right? How you actually can solve this thing, right? If you allow probability to work in your model, right? Just very simple idea. Is that okay? I know this is a very long topic. It's very complicated. I can't really talk too much, but you will see the first price option like this. The second price option is you would bid this, but you underbid 1 over NOV. Okay, so that is the main idea. Okay, and in some sense, you do see that when n is go to very large, okay, a lot of people bidding, doesn't really matter which format you're doing, right? In a large auction, doesn't really matter anyway, right? Because if many people bidding, you're not sure you're winning anyway. So that's not very strategic, right? Actually, it's a similar idea when you talk about Carnot, right? When the Carnot model, when n go to infinity, you get perfect competition, right? No need to be strategic, right? Somewhat similar idea here, right? When many bidder, that is not an issue, okay? So that's why the allocation problem in auction, usually you just have only very few buyers doing this, right? And that's why you see in the real world, right? Where the market has many participants, you don't really see auction, doesn't really matter anyway, right? You can just whatever, just try to do second price, first price, but doesn't really matter. Only when the case of n is small, yeah, you have to be careful. Okay. I don't think I have time to talk about this for double auction, but I will just highlight what it is. Okay. And double auction is frequently used in finance. Okay. And auction is like the IPO thing, right? For double auction is used in finance because the trading. In the auction model, the only thing that uncertain is the buyer, right? The seller doesn't know buyer valuation, buyer themselves they know, right? Right? There's no uncertainty on the seller, right? But double auction is there's uncertainty also in the buyer, so in the seller, okay? Which means that the valuation of the seller also follow some distribution, okay? And it need not always you want to trade, okay? And in this kind of setup, we focus on one buyer and one seller, okay? Usually, you can think of one firm and one worker, right? Or very often it's a supply chain, is an upstream and downstream, okay? And the question would be, okay, double auction is seller would try to limit price, okay? And buyer will also limit price, okay? Seller will be putting price they want to sell. Buyer will also put the price they want to buy, okay? And the game is such that, okay, there will be trade, okay? If there's a gap between the price, okay? Especially you need the, of course, the selling price, right? And the buying price, the buyer price is more, or the offer price is more than the asking price. Okay. Say suppose the sellers want to sell at least $5. The buyers want to pay $6, right? then there can be trade. And what price they trade is midpoint 550. Okay, let me repeat the statement. So you just imagine the following. Okay, put it this way. Okay, there's a guy who is the buyer. Okay, and there's a girl who's a seller. Okay, and the seller have a flower there. Okay, and his valuation maybe go from say 0 to 10. Okay, and the buyer want to buy the flower also 0 to 10. Okay, and the seller say, okay, I name the price P of the seller, maybe $5. Okay, the buyer say, I want to say the P of the B is say $6. Okay, maybe 7, maybe easier to think. $7. Okay, what happened to this is he's willing to pay more than you want to sell, right? The minimum price. So there will be transaction there, and there will transaction midpoint $6. Okay, but in the case that the boy only want to pay $4, then no trade. Okay, is that clear? So the only thing is different is now this guy valuation is also a changing, right? You can keep the object. It's also efficient to keep the object. So the difference is like this. Okay, there are two side asymmetry, and also the seller want to keep it. Okay, and this actually you can see the trading, right? Obviously, finance has a lot of paper on that. You look at supply chain is also something like this as well, right? Because you can imagine this is the supply chain, right? There's the upstream guy, the downstream guy, right? The producer is upstream, and then they want to negotiate what's the price there. Right? And as I said, right? If no trade is 0 profit, if trade according to just the subtraction, right? If they transact at $6, right? Right? Then it will depend on what kind of value they draw. Okay? Is that okay? And of course, you can solve for the same logic. You can try to solve the what the BNE is, right? It's just the buyer, right? His valuation minus the price he's going to pay, right? Because he's going to pay his proposed price and the price proposed by the seller, average of these two prices, and times how likely his price more than the seller price, right? Here is the seller would get is the transaction price minus his valuation, which is surplus, right? And what is the transaction price, which is the price he named and price the other guy named, right? Must be more than what he proposed, right? Half of that, and the probability that the buyer price higher than his price, right? And I'm not going to do the analysis because this model have many equilibrium potentially, right? Because on an auction, and I just go quickly. There can be single price equilibrium or linear equilibrium. So single price equilibrium will be some cutoff. Okay, so the buyer will say, if my value is more than x, x the same, so some value. Okay, x can be 1/2. Okay, any value from 0 to 1. Okay, say the buyer said more than 1/2, I will say 1/2. Otherwise, I said 0. And the seller will say, if my valuation is less than 1/2, I will say 1/2. Okay, otherwise at 0. And in that case, right, trade occur whenever this happens, right? That means that when the valuation of buyer is more than 1/2, is more than the seller's valuation, that will be trade. Okay, and this turned out to be a Bayesian Nash equilibrium because here remember that it will be a continuum of equilibrium. Okay, so x can be 0. Okay, actually x is 0 means that the buyer is not very serious. The seller is not very serious, right? Because the buyer, okay, whatever, I just give you 0. Okay, the seller said, okay, I'm not going to sell it. Okay, because it's double auction, right? They need coordination. If the buyer say I'm not serious, I always give 0 price, regardless of what. Nothing seller can do, right? It's more like coordination problem, right? Because it's different from the original case, the auction, right? The buyer can higher price, it will go into the sale, right? But in this case, is if they cannot coordinate, then there can be no trade, right? So that is something that any price is possible, okay? But they can coordinate at any price. Okay, can be anything from 0 to 1. Okay, so double auction means actually we don't have a nice prediction in some sense, right? Because anything is possible, single price. And actually we have more interesting thing is if we focus on the buyer and seller, okay, in general case you can say they just bid linearly, okay, and of course that you underbid, right? You bid more than your V anyway, right? So basically your strategy is like this, right? Maybe I just draw it here faster. So what you bid, right? If depend on your V or B, what actually your price, right? If you bid along this 45-degree line, then obviously you'll be stupid, right? Because you're going to pay more, right? Usually, right? Because this is the, so probably you would be bidding something like this, right? And this is alpha B, and the slope would be beta B, right? Somewhat like this. Okay, so the seller will be similar, right? So, and not going to the detail here. You can solve it as well. You can see how we solve it. I'm not going to detail, but then we go to the final answer. Okay, and turn out that oh, I don't have the graph here. And if you can see the main result is even the buyer valuation more than the seller, okay? If it's not more than 1/4 of it, there's no trade. Okay, that is the main result is if double auction, which is very natural, we expect, there will be inefficiency. Okay, you need the buyer have be sufficiently more than the seller. Trade can happen. Okay, and the reason for this inefficiency is because information asymmetry, right? If the information asymmetry is not there, right, and they will be settled with efficiency. But now because of I don't know, right, they have to work in a I don't know. They have to bid according to this kind of payoff bidding strategy, right? You try to bid two-thirds of your valuation, right? Same as this guy, right? So that's why this is the strategy like this one, okay? So they would bid two-thirds of the valuation plus different margin there, okay? So it turns out that there is the reason why they are not, I don't know, this thing happened, okay? So, and I would say this is double auction is a very big literature as well, especially for finance. Okay, but many of you are not doing finance anyway, so I don't want to spend time. For those who do finance, they will learn it in their own class anyway. Is that okay? It's okay. Let's have a 10 minutes break, and we will go to the topic 8. Okay. After break. So we left half an hour, and we are going to cover the most complicated topic. You know, it's impossible, but for sure, this is a very, very, very complicated item. And indeed, the literature, I don't think we have full understanding of what's going on here. At least in the topic, it's so complicated. And even you look at the games actually fully studied in this literature, they tend to be focusing on very simple cases. So that's why what we're doing. Okay. And the difficulties in analyzing this kind of model is the fact that people believe are endogenous. Okay. So that means that compared to the case in the topic 7 where belief is exogenous, here belief will be part of the equilibrium. In equilibrium, you need to specify what are the beliefs. Okay, so that is the key thing here. And belief actually have to evolve, and the evolution of belief, we will focus on the case where we will focus on the Bayesian equilibrium, which means that the belief had to be evolved according to Bayes' rule. Okay, so that will be the case. And I think we don't have time to cover many things. We focus on one of the most famous game is called signaling game. It is a case where the player who have private information move first, and his action would entail some of his private information. And the second guy who moved next will look at his action and try to make inference. Okay, and that will be the signaling game, and it applied to the span signaling model. Okay, so as I said, the belief is no longer static. Okay, the belief will change according to the history, according to what have been played, and the action can be informative or can be misleading. Of course, depend on whether their interests align, right? If the players' interests align, then there's no deceiving, right? They can just tell information with each other. The reason why this is important because there's a conflict of interest, right? Because of the interests not perfectly aligned, you would try to strategically manipulate the other guy, right? If you know exactly what happened, there's no exactly what is needed, right? So that is exactly what do you mean by a boy send a flower to girl, right? The boy send a flower to girl when boys and girl are in early relationship, right? Keep doing this, right? But once they got married, probably the boy stopped sending the flower because that's no longer mean a lot. But it may mean something, but it doesn't have to send this kind of expensive thing, right? That would be the thing. And actually today, I mean, when I come to school, I read an article which said a girl from China actually complained her boyfriend from Hong Kong. He tried to compare her boyfriend in China and compare boyfriend from Hong Kong. And they said boyfriend from mainland actually keep sending flower even for a very long time. But the Hong Kong boyfriend actually just sending for a few times and no more sending. Okay, so obviously there's some different kind of belief, right? The Hong Kong people think sending several times already signal enough, and that's done. Okay, and the boyfriend from China actually think that is not sufficient, have to keep sending flower. Okay, and also the girl also complained the China boyfriend allow allow her to check his phone all the time, but the Hong Kong boyfriend don't allow. Okay, I mean you can check. I mean this is a new complaint. I mean new hot topic in Hong Kong forum. Okay, but anyway, but this is basically the belief, right? Basically just like the boy try to send flower, which is expensive thing, which is usually have no economic value, right? It's only have signaling value, right? But the girl would think actually has important to keep the belief, right? Because the belief is you need to keep update. Okay. So you will see in this model, okay, you also have a set of player, self action, okay, and almost the same, right? That's not too much different from the what we have, okay. The only difference is we have what we call the P and I, right? Because the extensive form game here, we have probability from nature. This is the prior, right? Common prior, the P, small p, will decide what kind of type you are, right? It's a type idea. And information partition, right, or information set will tell you whether the player know where they are, right? So look at this game, okay? We'll do the game tree, okay? The only difference of what we have compared to the topic 6 and topic 8 is we have information set. Okay, the only difference is we have information set. Okay, and the thing here is player 2 doesn't know whether he's L or M. Okay, so player 1 can choose L, M, R. Okay, player 2, without knowing player 1 is L or M, okay, he has to choose L and R. Okay, so that's why you can see L prime and R prime the same. So you can only choose, player 2 only have two strategy. Okay, it's either L or R. Okay, he cannot choose L prime here and R prime there. No, he didn't know where he is. Okay, so that's the difference. Okay, you then look at how many sub games you have in this model. Only one sub game, right? Because if this is not one sub game, because you cannot cut through his game, so only one sub game. Okay, and the question of what kind of equilibrium you have, okay, and you can check because you can just write a matrix there, okay, and okay, you can write. Did I write that down here? No, I didn't. So how do you solve this game? Player 1 you have L, M, R. Player 2 you have L prime, R prime, right? And the payoff of L prime is 2, 1, right? L, R prime is 0, 0. Maybe I just write 2, 1 is enough. 2, 1 and 0, 0. Okay, and 0, 2, 0, 1, and 1, 3, 1, 3. Okay, because only one subgame. Okay, so that's why Nash equilibrium is also subgame perfect, right? So what is the outcome here? 2 is better than, suppose player 2 choose L prime, player 1 choose L, right? It's the best response. If player 2 choose R prime, player 1 choose R, right? So look at player 2 perspective. If player 1 choose L, player 1 choose L prime, right? And with player 2 choose M, player 1 will choose L as well. If player 1 choose R, player 1 will choose 3 is the same. Okay, so the mutual best response turn out to be this outcome and this outcome, right? So that's 2 Nash equilibrium. Okay, and the thing is, okay, is the 2 outcome equally plausible? Okay, I would argue that, okay, choosing, compare this, choosing L prime is better than R prime, right? No, choosing choosing L prime is better than choosing R prime. Why? Okay. Okay. So the question is, why you would choose R prime? Okay. You choose R prime because actually it's here, right? And you can imagine that if player one actually choosing, you actually have to choose here, right? It must be player one choosing L and M, right? It must be the case that, I mean, yeah, for him to choose this one, you should have here, right? So it's like this is sustained from the fact that actually the game is happened here. Nothing is optimized in this way. Okay. And is there any reason to believe that player two to choose R prime? I mean, his belief is payoff is like here, right? Or here, right? His payoff is either 0 or 1 here, right? If he chooses RL, L his 1 is better than 0. 2 is better than 1, right? So doing R prime is actually dominated, right? If he has to, his decision has to make sense, right? He shouldn't allow player 2 to choose R prime, because R prime is something stupid, right? If forget about this, right? R prime is stupid, right? R prime gets 0 compared to 1. R prime is stupid compared to you get 2 rather than 1, right? So why we believe that R prime is the right thing, right? There's no way you can say choosing R prime is any reasonable choice. Okay. So that's why we talk about in this dynamic game, you have to include belief in the system. Okay. You have to say in equilibrium, what player two think where he is. Okay. What probability is here is here. In this particular case, no matter what kind of probability you put, that's not possible to choose R prime. Okay. So the thing is, you need to assign probability to his information set. You tell them, okay, what is your belief whether you're here, you're here? Okay. In that case, even though in equilibrium, this is what we call the off equilibrium path, right? It's not equilibrium exists. It is still doing the right thing. Okay. So to reiterate why we need to put belief on here is because subgame perfection, as you see, is not sufficient because it cannot cut through here, right? It cannot have a subgame is here. Okay. So that's why the way to solve this problem is we have to take belief. Okay. We make sure that player two under equilibrium we have to assign where he is. Can be equal, can be 1 0 or 0 1, or can any probability assigned here to here. But then can justify his choice of R prime. Okay. So let's see how we do it. Okay. So that's why what we call perfect Bayesian equilibrium, okay, is the fact that, okay, you need to have a system of belief, means probability, assigned in every node in the information set, okay, and what you're doing have to be best according to what you believe. Okay, the second one. The first one is you have to believe all the information set. The second one is you are acting on your belief. Okay, it's a reason based, right? What you're doing is based on some reasoning. Okay, and your belief has to be rational. Okay, we'll define it very soon. What is rational? You will see that means the base rule. Okay. So what is the how do you define the Bayesian Nash equilibrium? Okay, is besides action, you need to tell me what is the belief. Okay, in this model. So suppose I choose LL prime. Okay, suppose the easiest case LL prime. Okay, what should be your belief according to the base rule? Okay, 1 choose L, 2 choose L prime. Okay, so what should be the belief? Okay, this is chosen, and this is chosen. Okay, of course this is chosen as well. Okay, so because L has chosen, right? That means that if you play this game many times, it's always you see this one, right? So how you have the belief? Assuming you play this many times, your belief should be you said 1 here, 0 here, right? You just imagine that if this game play many times, you all the time you see L comes in. So what is expectation? If you play this once more, it must be you only think you're only in the left hand side, right? So just that's the belief, right? And if player 2 think this is 1, this is 0, what you should do? Right? You're here, right? Then you just compare 1 or 0. That's 1. Okay. So your action is optimal given your belief, and your belief is assigned to the information set. Okay. So everything is this is a perfect Bayesian equilibrium. Is that clear? So the only additional thing compared to subgame perfect is you have to tell me where you are, and where you are, your belief has to be consistent with the action. Okay, and we try to argue that there's no P. Okay, there's no P such that you believe you can choose R, right? Because if you choose L, okay, what's your payoff? Will be P times 1, right? And 1 minus P times 2. Okay, so this is the expected payoff if you choose L prime, right? And if you choose R, right, it's P times 0 plus 1 minus P times 1, so 1 minus P, right? So if you need to say choose R, it must be the case that the expected payoff of R more than L. And if you try to see this, impossible, right? So there's no P you can support this. So you will remove this not reasonable equilibrium, right? Because you are choosing a dominated strategy, right? So we are trying to remove the idea that it's dominant strategy, but this is according to within the information set, right? So this is not reasonable. That's how you derive this. Okay. Now, I hope I convinced you here. So let's see the example. Okay. And as I said, we'll focus on several types of games. And as I told you, in the literature, people focus on several special games. Okay. And they don't go into much detail because in general, each game is very different. So you have to do each game separately. Unlike Nash equilibrium, is even much easier. You can do a general analysis. But this one is highly dependent on your setup. Okay. So signal game is very simple. As I said, the 2 players, sender, receiver. Okay. And sender move first. Okay. Sender move first, and he has information advantage. Okay. And what he do is he send some message, right? As I said, boy and girl. You can imagine that our receiver is the girl, the boy send a message. Okay, the boy know whether he like the girls or not, really like her or just normally like. Okay, and he also send a message. Okay, and and A with action, the girl decide whether maybe go to date with him or not, right? The boy will be J. I send a message with flower, or I don't send, I just send a WhatsApp. Do you want to go out? That's it. Okay, 2 messages. And the girl will say, where do you want to go, right? The girl probably will go to with the boy. If the boy really like her, it's a good one. If not, then it's not good. Okay. And then the type, right? The type we just say only the boy have private information. With the boy actually is a good boy, right? Maybe the boy has a lot of money, or the boy will like her. There's different types. Okay. P will be coming from some prior. Okay. Later you will see what do you mean by that, and there's some payoff. Okay. So let's see the example, and then you will see. Okay. Again, the game is the following. Nature will draw the probability, right? And it's very likely the boy is a good boy or the bad boy or the playboy. Okay. And he learned whether he's a real serious guy or a playboy, and then send a message, okay, to a girl. And a girl take a message whether we go date with the boy or not. Okay. And then this is the payoff. Okay. So this is the structure. But don't worry, let's see this is usually the graph that you would see. Okay. Nature, how you read this diagram, start in the center. Nature. Either he's a good boy or playboy. Okay. And good boy he can do is like send a WhatsApp or WeChat message. Hi, go out. And 2 is, hi, see the flower, let's go out. Okay. And the girl doesn't actually see whether he is a good boy or playboy, right? And then we say, okay, go out or stay at home. Okay. This is the game. Okay. Is it clear what the game is? Okay. Nature move first. Nature decide playboy or good boy, playboy. Okay. And decide what kind of message going to send the girl. The girl doesn't see, and he had to decide what the action is. Okay. And that's the model. Okay. And first, we need to have system of belief. Okay. For the requirement. Okay. So you need to, what they mean is, in equilibrium, we have to say girl have to put probability here and here, sum to 1, same as here. Okay. So it's system of belief. Second is sequential rationality. Is given the belief the girl is doing the right thing, and boy is also doing the right thing, given send the right message, right? The girl is doing the best thing based on the belief. Okay. And the next one is, if you suppose you repeat this game many times, okay, and you should expect your belief will be aligned with what it happened. Okay, don't worry. This looks not so natural, but when you do it, it's very simple. Okay, don't worry. We'll just go to example. You see what do you mean by that. Although this looks crazy, I think it's very crazy. When at first I learned it, I don't know what's going on. I mean, what is this? Okay, don't worry. We go to the example. You do it, and you will see what is going on. Okay. So usually, in terms of solving the model, usually focus on 3 different cases. One is separate equilibrium, which means that good boy will send a message with flower. Playboy will just send a message. Or vice versa. Different types of boy will send different types of message. Pooling means that they can't tell. Playboy and the good boy, they do the same thing. Okay? Or the other way around, hybrid. But we focus on these 2 cases because this is what the literature usually doing. Okay? So let's see the example here. Okay? Here is equally likely to be a playboy or the good boy. Okay? And they send a left message or right message. Okay? And left here, he will have to decide up or down. Right? Up or down here. Okay? So this is the payoff. And if the right is, this is the number. Okay? We will go one by one, so don't worry. Okay? Let's see the following. Okay? How we do this is how you solve this problem is we will assume, okay, we'll check all possible scenarios. Okay, first let's do the cases. They send separating message. What do you mean by that? Okay, so assume the type 1 they send L, type 2 they send R. Okay, suppose this is the equilibrium. Okay, suppose this is that, right? So what would be the belief? If this repeat many times, the right belief will be this is 1, this is 0, right? And this must be 1 and this is 0. Is that clear why this is the belief? Right? If you imagine this game played many times, if you know what happened, right? Every time you know what actually happened, this is what you should expect, right? And now we consider sequential rationality. Okay, what do you mean by that? Means girl think he's here, right? So girl look at 3 and 0. What he will do? He will do the U, right? Is that clear? So actually, he don't know if actually here is also U anyway, right? Because he don't know where he is, right? That's U. If R, he will choose compare 2 and 0. Right? He will go to D, down. Same for this one. Okay? So this is optimal for this thing happen. Okay? What remains to check is the boy doing the right thing? Okay? The boy is here. Okay? The boy is here. If he go to L, the payoff is 1. Right? If you go to right, this is 0. Okay? Doing this is right. Now look at the lower type sender. If you go to right, the payoff is 1. Right? And if you go to left, the payoff is 2. So go to this one is not right. Okay? So this is not an equilibrium. Is that clear? Because play of this type is not going to send this message as we propose. Okay? So now, is that okay for this one? Now then we check the other case because we need to check many cases. The other case is player 1 choose R here, player 2 choose L here. Okay? And in that case, if you may play many times, this is 1, this is 0, right? This is 1, this is 0. Is that clear why this is true? Is that okay? Because there's no mistake, right? You see L, when the receiver see L, it must be coming from the lower guy, right? There are no consistent mistake here. That's the base rule here, right? Your action, your belief derived from your action in equilibrium, okay? That's the base rule set. So under your belief you are here, you compare 4 and 1, that's why up, right? Actually same here. And if you know now you are in the R, then you compare 1 and 0, that's why you have U. Okay? And the next thing is, okay, player 1, if you go to R, payoff is 2, and the payoff is here is 1, so 2 is still better than 1, so this is fine. Okay? Look at here, player 1 payoff is 2. Oh, sorry, I forget the red here. And player 1 gets 1 here, so this is still right. Okay? So because 2 is better than 1. Okay? So this is a Bayesian-Nash equilibrium, perfect Bayesian equilibrium. Being the player 1, if you are type 1 R, then player 2 you get type 2 you get L. And the belief of the sender, the receiver will be I see L, it must be type 2. And I choose up. If I see R, it must be type 1, and I choose up. Okay, so this is what the result is. Is that okay? Now this is one equilibrium. Okay, and I want to show the other equilibrium. So this is already written down here. Okay, and we look at the oh, I think, sorry, it's already done here. So anyway, yeah, so I done that. Yeah, I didn't need to write that. Okay, so the other is the pooling equilibrium. Okay, so both case is going to be L. Okay, so maybe I go from beginning, that would be better. Okay, so how can I do this? Okay, so first is we can start with the cases. Both case is going to be L. Okay, so consider case both type 1 is L, and then we try to see, does it make sense? Okay, the question is, if all the time I saw both guys are sending L, what should be my belief here? Do you learn anything? You learn nothing, because both of them send the same signal. So your belief will just follow what you believe at the beginning. So there's no learning. So which means that the action doesn't teach you anything. Okay, if both boys are sending flowers, what's going to learn? Nothing, right? You're not going to learn anything about whether they're a paid boy or good boy, right? In that case. Now, given is half and half. Okay, so what is the optimum thing to do? Okay, if player 2 choose up, is half of them is 3, half of them is 4, so it's 3.5, right? Half of 3 times half of 4, which is 3.5. Okay, and if you choose low, then you will be 0 or 1. Half of 0, half of 1 is 1/2, right? So the optimal way to do things is just go to up, right? Right, because up it gives you half of 3 or half of 4. If you do down, it's half of 0, half of 1. Is that clear? Is that okay for this one? Okay, so up is the right thing. And okay, so the question is, how do we decide this one? Okay, how can I do this one? And base rule doesn't tell me anything about it. Okay, the only thing we require is just they add up to 1, right? As long as the system belief is fine. Okay, so that means that there are two scenarios. Scenario 1, maybe just choose U. Okay, choose U will give you payoff of Q of 1, right, times 1 minus Q of 0, right, 1 and 0. If you choose down, the payoff will be Q times 0 plus 1 minus Q times 2. Okay, so it's 2 minus Q, 2 minus 2Q here, and the red will be just Q. Okay, so if you want Q to be chosen, right, up to be chosen, right, if you up is the equilibrium, it must be the case this is bigger than this one, right? So it must be the Q is bigger than 2/3, right? That means that it's more likely to be up rather than down, then you choose up, right? If less than 2/3, you choose down. Okay, so there are two scenarios. Now we do one by one. So let's focus on the case where this thing happened, right? They believe this, up is chosen. Okay, and in that case, right, so what is the choice? Player 1, if choose L, okay, the payoff is 4, right? But the other Y is 2, so this is fine, right? Player 2 would choose U, the payoff is 2. Okay. If I choose this one, okay, it's 1. Right? So this is still okay. Right? So that's why player 1 choose, both of them choose L with this belief. Player 2 always choose U. It's fine. This belief, there's no problem. Is that clear? Okay. So although this looks ugly, so that is what it is. Right? Bigger than 2/3, this is justified. Okay. And I don't want to take you too much time, so I just talk about the last game and that's it. Okay. But in general, this is the same thing. Okay. And if you less than 2/3, right? And this with D chosen, only thing to check is whether player 1 is happy, right? Player 1 is getting 1 here. If you deviate, you get 0. And player 1 is you choosing L is getting 2 here. If you deviate, you get 1. So still fine. Okay. So everyone is doing the right thing. That's fine. Okay. And because it's chosen here, so you actually don't know this is not realized in equilibrium. So the perfect Bayesian equilibrium means if equilibrium does nothing arrive, you allow anything can be done here as long as up to 1. Well, because you don't know, because you don't learn anything because they choose here. So it means that you never okay. There's nothing in the history observed R. So what is your belief? You cannot tell. Okay, of course you will say whether this Q is 2/3 or 1/2, is it more reasonable? That's another issue. But in this case, we don't put any reflection. That's what the perfect Bayesian is if it's not arrived there, anything you can assign, as long as this is up to 1. But I mean, of course, if you have a what we call the sequential equilibrium or other equilibrium, then there will be more. But the perfect Bayesian actually don't have anything. Just you allow anything happen as long as more than 1, up to 1, fine. So and as I just use 1 or 2 more minutes, I'm not going to talk about it because the time constraint. And the Spencer-Lane game. So what in this game is worker have different ability level, and what you're doing is try to tell the firm I'm capable. How can you do that? Go to school. Okay, school is costly. If you're smart, go to school is cost less. If you're dumb, then not so smart, then you would take more cost to you. Okay, so you can imagine that there will be equilibrium, depends on what you see. You will see, okay, it's possible that everyone go to school, get higher education, then the degree will be useless, right? You get an average salary, right? Or now you got the Ph.D, you distinguish from the others, right? So you get some pooling equilibrium, some separating equilibrium, so on and so forth. Okay, and I guess I don't have enough time to talk about it. But at the end, one interesting thing is if what this model would say is if you look at the perfect Bayesian equilibrium and impose some restriction further, you expect pooling equilibrium to exist. Pooling equilibrium is gone. So there are no way the high type and low type the low type cannot pretend high type. Okay? So that is one of the main outcome of this model is because you're pooling, right? Because basically the low type is the high type. High type is not very happy, right? So everyone go to college, right? These days, right? So you cannot get extra wage premium. So what do people do? Study master, study Ph.D, study postdoc, study another postdoc, right? In that case, no one is going to continue with you, right? So it can earn premium, so separate. So that is the main result, is you impose more restriction, more refinement for interior refinement, many more refinement. End up is you don't have any pooling equilibrium. End up is must be separate. Okay, so that's the run result, is you have to impose further restriction to make this thing happen. Okay, and I think this is a very famous paper, Spence. Even though I think if you don't learn anything in the grad school, undergrad will tell you this is a kind of model. I mean, I'm sorry I don't have enough time to cover, but I think you can just basically, there's no different from this model, right? Nature decide you are smart or not so smart. You go to educate or not educate, and the payoff is higher you, right? Different wages, right? If you see the high school diploma, what high wage, low wage, right? So on and so forth, right? So same idea, okay? But I don't think we have time to go over. But I guess this is already sufficient, because you will see the same proof. But I can't. We don't have enough time. So thank you for attending. Good luck. I will put the test today or tomorrow on the blackboard. You can take your time. I think the deadline is like 5th of December. I put there. Okay, you have more than 1 week to do it, but you should spend 3 hours to be sufficient. Okay, and just don't discuss among yourself. Just do it by yourself. Okay. So thank you. I see you in the future.